Hi, I'm Michelle Johnson, Public Affairs Manager here at NASA Ames Research Center in California, Silicon Valley. Today we're here to hear the latest results from NASA's exoplanet hunting mission, the Kepler mission. We have 4 panelists here today to share the latest results, and we'll be addressing our live audience as well as those on the phone. For those joining on Ustream, there will be a 30-second delay in the stream from what's happening here in the newsroom. For all the graphics that the panelists are using, you can go to the web at www.nasa.gov/Kepler. So the panelists will each give their short briefing, and then we're going to switch to Q&A. We'll take our live audience first and then go to the phone. And then for you, those of you following on social media, you can ask your question via Twitter. Tag your question with hashtag #AskKepler. The media briefing will be limited to 1 hour. Today's panelists are Mario Perez, Kepler Program Scientist in the Astrophysics Division of NASA's Science Mission Directorate in Washington, D.C. Susan Thompson, Kepler Research Scientist at the SETI Institute in Mountain View, California, and here at NASA Ames. B.J. Fulton, doctoral candidate at the University of Hawaii in Manoa and at the California Institute of Technology, or Caltech, in Pasadena. And finally, we have Courtney Dressing, NASA Sagan Fellow at Caltech. So with that, let's start it off. Mario?
Thanks, Michelle. It is indeed a pleasure to introduce this NASA Kepler release that describes the most recent results of the survey catalog of planet candidates. This Kepler candidate catalog contains the best measure and the most reliable data that we believe that could be planets. From this new data, we report today that there are 219 planet candidates, of which 10 are possibly rocky and the habitable zone of their star, which is a region of distances from a star where liquid water might appear on the surface of a rocky planet. Next slide. Kepler, which was the first NASA mission capable of detecting Earth-sized planets, make this detection via the transit method, which is a photometric technique that measures the minuscule dimming of starlight as a planet passes in front of its host star. This motion is animated in this graphic. This new result presented today have implications for understanding the frequency of different types of planets in our galaxy and help us to advance our knowledge how planets are formed. Next slide. Kepler spent the first 4 years of his primary mission observing one single star field located in the Cygnus constellation. This new result of exoplanet presented today comes from continuous observation of the Cygnus field indicated on the left of this illustration. Kepler keeps taking data today, and for the last 4 years has been on a second mission named K2, observing fields on the ecliptic plane of our galaxy. Next slide. Kepler has been the most productive spacecraft in detecting exoplanets. Future missions like Transiting Exoplanet Survey Satellite, or TESS, launching in 2018, will detect new exoplanets around bright and nearby stars via the same transit method used by Kepler. W-FIRST, launching in the mid-2020s, will further contribute to discovery and characterization of exoplanet populations. Even beyond the Kepler era, NASA will continue to search for new worlds and for signs of life beyond our solar system. In summary, including the new results announced today, up to now, Kepler has identified 4,034 planet candidates orbiting other stars, and there are 2,335 confirmed planets. Of all the planet candidates and confirmed exoplanet, Kepler has discovered more than 80% of them. Thanks.
Thanks, Mario. Joining us from the SETI Institute to tell us more about her work on the final Kepler candidate catalog is Susan Thompson. Susan?
Thank you, Michelle. I'm here today to announce the final Kepler survey catalog of planet candidates found from the Cygnus field. This is the first 4 years of data that Mario just talked about. This is the last search that we performed, and we used our most improved techniques. And with that, we found 4,034 candidates, which include 10 new terrestrial-sized candidates in the habitable zone of their star. This catalog is truly unique because for the first time we have characterized the catalog, and as a result, it allows us to do a direct survey of Earth analogs in this part of the sky. So we go to the first slide. I'm plotting here our high confidence planet candidates. Along the x-axis, you see the orbital period, and along the y-axis, you have the size of the planet relative to Earth. There are 3 horizontal white lines showing the sizes of Jupiter, Neptune, and Earth for reference. What you can see here is that most of the planets found by Kepler are smaller than Neptune. And Kepler really, truly has opened up our eyes to the existence of these small terrestrial-sized worlds. Now, if we go to the next slide, I highlight the 219 new candidates found in this catalog. Most of them are small, less than 3 Earth radii, and several of them lie even out at long orbital periods, near to the orbital period of the Earth around the Sun. However, for this last catalog, we're turning our attention away from finding these new individual systems and towards trying to understand the demographics of these worlds that are most similar to our planet Earth. To describe how we did that, if we move to the next slide, I need to tell you a little bit about how we go about doing our search. Using our most discerning software, we searched the 200,000 stars observed by Kepler. This process is entirely automated and uniformly applied to all the data that is sent through the pipeline, which we're representing here with a simple blue triangle. After we searched the stars, we found about 34,000 signals, and these signals contain our transiting planets, but they also contain a lot of noise, either from the camera or from the stars. We then used a tool called the RoboVetter to scrutinize each and every one of these signals in order to find the candidates, the planet candidates, which create the catalog. So it found about 4,000 candidates, 50 of which are terrestrial sized and in the habitable zone of their star. However, we didn't stop there. We needed to characterize our catalog. And as a result, if we go to the next slide, you see we injected simulated transits. We put those through the same pipeline. And we determined how often we missed finding those particular transits. And as a result, we measured the undercount of our survey, or the catalog completeness. And then finally, we also put through simulated noise on the next slide. And you can see here that if we went through, as we put the noise through, we counted how often we mistook noise as a transit. And as a result, we measured the overcount of our survey, or the catalog reliability. So if we go to the next slide, with this catalog, we were able to even examine planets that were found in the habitable zone of their stars. So plotted here are the confirmed planets that we have found in Kepler's habitable zone. All of these are terrestrial size, less than 1.8 times the size of the Earth, and lie in their habitable zone, at least within their measured uncertainties. Along the x-axis, you actually have the energy received by the planet. So the warmer planets are on the left-hand side. They're closer to their star. And along the x-axis, you have the temperature of the star, with the cooler stars at the bottom, and those stars most similar to our sun at 5,800 Kelvin towards the top. We show Venus, Earth, and Mars for reference, and notice that the habitable zone, which is highlighted in green, runs from approximately Venus to Mars for sun-like stars. Because the habitable zone is much closer to these smaller, cooler stars, it's much easier to find those planets, and that's why most of our confirmed planets are around these small stars. But now if we add in the candidates that were found in this catalog, which are shown in yellow, you can see that we fill in the population of planets around sun-like stars, those at the top of the diagram. For instance, if we go to the next slide, you can see the ones that are brand new to this catalog. And the closest Earth analog we have of these high confidence candidates from this catalog is KOI 7711. It sits right next to the Earth on this diagram, meaning it receives just about the same amount of energy as we do from our sun. And it's only slightly larger than the Earth at 1.3 Earth radii. But what's also important, besides finding these interesting new systems, is that we have characterized how many planets we missed in this region and how many of these planets are likely due to noise. And as a result, we are able to extend the ability to do demographics from the habitable zone of just the smallest stars out to even those stars similar to the sun. So I will leave you with the last slide, which again shows our planet candidates, and point out that we have done this sort of demographics of exoplanets out at shorter periods. But now with this catalog, we're able to extend that out to the longest periods, those periods that are most similar to our Earth. And so as a result, this survey catalog will be the foundation for directly answering one of astronomy's most compelling questions: how many planets like our Earth are actually in the galaxy? Thank you.
Oh, thank you, Susan. Now here to tell us about his work measuring the demographics of the smallest planets in the galaxy is BJ Fulton. BJ?
Thank you, Michelle. Yeah, so I'm going to be sharing a very exciting result that was made possible thanks to the catalogs of thousands of Kepler planets like the one that Susan just described. We've just discovered that what we thought was a single type of planets is actually two distinct classes of planets with quite different properties. Next slide, please. Before our study, the Kepler mission had already demonstrated that small planets between the size of Earth and Neptune are both common and diverse. Here I'm showing the number of planets per 100 stars for a range of different planet sizes. On the left are planets the size of Earth, and on the right are planets the size of Jupiter. Now you see at around 4 times the size of Earth, or about the size of Neptune, the number of planets shoots up drastically. Next slide, please. So in order to resolve fine details in the radius distribution of planets, our team embarked on a 5-year campaign with the Keck Observatory to characterize over 1,300 stars known to host Kepler planets. Since the transit technique used by Kepler gives us a way to measure the the planet size relative to the star's size, by precisely measuring the stellar sizes, we greatly enhanced our knowledge of the planets. Armed with a precise catalog of Kepler planet sizes, we examined the family tree of small planets. Kepler planets had appeared to span all sizes between 1 and 4 times the size of Earth, but when measured precisely, small planets design into 2 distinct size groups. Next slide, please. Most of the planets in the first group may be akin to the Earth, with rocky surfaces and little to no atmospheres. Planets in the second group are probably more like cousins of Neptune's, with thick atmospheres and no surface to speak of. Intermediate-sized planets between these 2 size groups are relatively rare. This is a major new division in the family tree of exoplanets, somewhat analogous to the discovery that mammals and lizards are separate branches on the tree of life. We can speculate as to why nature prefers to make small planets in these 2 sizes. Next slide, please. So the size of the planet is determined by the quantity and the type of materials that are gathered together during the planet's formation. Planet sizes can also change with time if materials are stripped away. The size of the planets in the first group suggests that Earth-like rocky planets can typically be no larger than about 75% bigger than the Earth. A very small amount of light, hydrogen, and helium gases goes a long way to inflate the size of planets. Adding a tiny amount of hydrogen to one of these rocky planets, say about 2% by mass, would cause the planet to jump the gap and move into the group of larger planets. Planets need to have a very finely tuned amount of hydrogen and helium to live right in the middle of that gap, between about 0.1% and 1% of hydrogen and helium, and that just doesn't leave much wiggle room. The gap between the 2 planet sizes also suggests that environment plays a decisive role. The atmospheres of planets orbiting close to their host stars are susceptible to being blowtorched away by the extreme radiation from the star. After millions of years, the slightly larger gaseous planets that we see today either needed to start with very thick atmospheres that could survive the erosion or grow up in a more benign environment farther away from their host stars. The few planets that may have started off right in the middle of that gap with just the right amount of hydrogen and helium are prone to losing all of that hydrogen and then moving down into the class of smaller planets. This result has significant implications for the search for life. Approximately half of the planets that we know are so common have no solid surface or a surface deep beneath the crushing weight of a thick atmospheres. And these would not be nice places to live. Our result sharpens up the dividing line between potentially habitable planets and those that are inhospitable to life as we know it. Thank you for your attention. I'll give it back to Michelle.
Thank you, BJ. And to share her perspective on the results from the Kepler mission that you've just heard about is Courtney Dressing from Caltech. Courtney?
Thank you, Michelle. We've heard remarkable results today. From Susan Thompson, we saw the latest catalog of Kepler results. That catalog of 4,034 planets includes 219 new detections and 10 possibly habitable worlds. From BJ Fulton, we learned that planets with radii between 1.5 and 2 Earth radii are scarce. Most planets are either larger than that number or smaller than that number. They're either like the Earth or like Neptune, but not so much in between. Going to the next slide, I want to take us back in time to 2009, before the NASA Kepler mission launched. This is what we knew about exoplanet populations back in 2009. On the left side of the plot, you see the size of the planet relative to the Earth. The white horizontal lines indicate the sizes of Earth, Neptune, and Jupiter for scale. On the bottom of the plot, I'm showing you the orbital period of the planet, or how long it takes it to go around its star. What you see on this plot is that we knew about planets with a wide range of orbital periods, but we didn't know of very many small planets. Most of the worlds on this plot are Jupiter-sized, maybe even a few are Neptune-sized. Very few are small worlds like the Earth. Advancing forward to after Kepler found planets, we see on the next slide that there are now thousands of yellow dots. These worlds were found by Kepler during its study of the Cygnus field. From BJ, we learned that that population of yellow planets hovering between the Earth line and the Neptune line actually divides nicely into two populations, one smaller than 1.5 Earth radii and one larger than 2 Earth radii. This sample of planets is quite unique and allows us to do sophisticated statistical studies. As Susan pointed out, this latest version of the Kepler catalog was found in a uniform way using sophisticated robo-vetting tools, which means it can be used for statistical analyses to answer questions like, how common is the Earth in the galaxy, and how many solar systems are like ours? On the next slide, I've highlighted several populations of planets that we've learned about from Kepler and other missions and surveys. What we see here is different populations with different colored ovals. On the top, we have an oval in the top left for hot Jupiters, worlds like Jupiter that are closer to their star than Mercury is to the Sun. On the top right, we have another oval for cold gas giants. Those are worlds analogous to Jupiter in our own solar system. Below that, we have the ocean worlds and ice giants. These are the planets that are just on the other side of the gap that BJ Fulton described. Below that gap, we have a large yellow oval showing all of the rocky planets that potentially could be like Earth. Most of the ones shown on this diagram are probably hotter than the Earth, but the ones towards the right end might actually be cool places to live in the future. The ones in the green oval are the lava worlds. These planets are like Kepler 10b. They're so close to their stars that their surfaces are covered in molten lava. Those would not be good places to live. In the lower right corner of the plot, we see the frontier. This region does not have very many exoplanets in it. We also see a region at the middle left of the plot that doesn't have any exoplanets. But the reason for the absence of the planets in those two regions is different. On the left side, we don't see exoplanets there because they're quite rare. In the lower right corner, however, we don't see exoplanets there because they're very difficult to find. Kepler has been pushing the boundary of the frontier towards the right corner of the plot. Kepler has pushed us towards smaller planets and planets in longer period orbits. As we go forward towards the future, that frontier will continue to advance. On the next slide, we see here the chart that Mario showed earlier. This is the progress of NASA exoplanet missions through the decades. Here we're focusing today on the results of the NASA Kepler mission. Next year, in 2018, the Transiting Exoplanet Survey satellite will launch and begin detecting planets around bright stars. Bright stars are fantastic for planet detection because those stars are well suited for follow-up observations that could reveal the mass of the planet from the ground. After tests, we'll be able to characterize the atmospheres of planets using the James Webb Space Telescope and find even more planets with W first. Looking forward to the 2030s, we can imagine the day where we actually take direct images of planets like the Earth in the habitable zones of sun-like stars. I can't wait to see the press conference that will occur once those missions are flying. Thank you very much.
Thank you, Courtney, and neither can I. Well, let's turn to questions and answers now. We have several reporters here in the live audience and a number of you on the phone as well. And for those joining in on Twitter, we're going to have you ask your question first with hashtag #AskKepler. With the number of folks queued up to ask questions, we're going to give everyone a chance to ask one question and a follow-up, and then if time permits, we'll go back and start again. Our operator will identify you by name, but if not, please give your name, your media affiliation, and direct your question to a panelist if possible. For those dialing in, please push star asterisk on your phone to get in the queue to ask a question. And with that, we'll look for questions here in the audience first. And we have a mic coming to you right now, right behind you.
Thank you. Rob Reynolds from Al Jazeera English. So if you could break it down for the layman's audience, how many planets have you discovered in total? And how many of them are in this Goldilocks zone that might support life? And I have a follow-up question.
Excuse me. With this, sorry, your first question was how many we discovered in total?
Yes,
And
with Kepler, I
yes,
should
Kepler
add.
has confirmed over 2,300 planets, and these are planets where there is no question at all that that signal is coming from an exoplanet. What I'm presenting here today are candidates, meaning there's still some room for doubt whether that signal is coming from a planet. It could still be coming from other astrophysical signals. So this catalog, though, has 4,034 candidates, and that's a pretty close number to the final Kepler candidates that will be found. We may clean up a few more in the end and find a few more in the end, but this catalog has 4,034.
And in the Goldilocks zone?
We have approximately 50 that are in the Goldilocks zone.
My follow-up question is, as I understand it, Kepler is focusing on a very small.
Yes, I should
Well,
clarify that was 50 terrestrial-sized planets in the Goldilocks zone.
terrestrial-sized planets that are in the right.
Right, so small
Not too
planets
hot,
that
not
are
too
in the
cold.
Goldilocks zone. We have
Great.
more that are that are larger.
That the telescope is focusing on a relatively small area in the Cygnus formation, right? So based on that and whatever statistical analysis you've been able to do, how common are the potentially rocky, in the right zone, habitable zone planets in our whole galaxy? Any ideas?
So we still haven't done that analysis on this specific catalog. Courtney might want to address some of the other studies that have been done previously.
Sure. For M dwarfs, which are small stars that make up 75% of stars in the galaxy, we know that 1 out of every 4 of them has a planet that is small and is in the habitable zone.
How many does that make?
It means that it's not crazy that we found a planet in the habitable zone of the closest star to the sun. So Proxima Centauri b has a small planet in the habitable zone. At least we think it's small. It does not transit, so we do not know the size of the planet for sure, but the mass measurement's consistent with it being small.
How far away is that?
It's very close.
I'm sorry, I'm not, sorry to prolong my question and answer period, but how close is close in terms of light years?
Just a couple.
Just
It's
a
right
couple
next door.
Right next door. And there could be life on it.
We'll have to find out. It's something we could try to do with the next generation of ground-based large telescopes.
Thank you.
All right, thank you. We have another question here. We'll bring a mic to you.
Hi, Allison Hawks from Astrobiology Magazine. Just wanted to know about tidally locked planets and if you've been able to understand a little bit about, which of these terrestrial planets might be tidally locked and what the implications then are for habitability in those cases.
Planets around low-mass stars tend to fall within the tidal locking radius because they're so close to the star you might expect them to be like the moon with one side always facing the star. Back in the day, people thought that would be bad for life because the atmosphere could freeze out if one side of the planet was very cold. More sophisticated three-dimensional models have revealed that if the planet has a bit of an atmosphere, it probably would stay warm enough to remain hospitable to life. And there's a chance then that you could have a bunch of civilizations where maybe all the astronomers live on one side of the planet and everyone else enjoys the sun side on the beachy side close to the star.
All right, let's take a couple questions from the phone line. Alicia, who do you have lined up for us?
The Associated Press. Your line is open.
Yes, thank you. I have one question and then a follow-up. Let's look at these new planets, the 219 new planet candidates and the 10 roughly Earth-sized ones in the habitable zone. Am I right in hearing that those 10 are in some ways different than many of the other ones because they're aren't most of them sort of more G dwarfs like the Sun instead of the M dwarfs? I mean, in other words, are these 10, how many of them are sort of more Earth analogy, and does that make them more important, and what does that mean? And then I'll have a follow-up.
So you're asking about the 10 planets that are around in the habitable zone, and those that are near that orbit a star similar to our sun. The thing about stars similar to our sun, they're not nearly as active as those that are around M dwarfs, and Courtney probably could talk more about that. And as a result, we know that there is life on planets around G dwarfs. We have it here, and so that's partly why we focus in on looking for planets that are in the habitable zone of G-type stars, or our sun-like stars. Sorry. To remember the rest of that question. So that is what's unique about those new ones that are found. What is also unique is that I can tell you with high confidence that those are really signals in our data that they're truly astrophysical, unlike some of the other candidates we've released.
Thank you. Did you have a follow-up?
Yes. Okay. One of them is, how many of those 10 are G dwarfs? Are they all? And then what? I know you haven't done the overall census demographic issue, but that's sort of what Kepler was sold to the American public as it is a demographic. So can you give us, I mean, just looking at the math, it looks like 1 out of 80 stars, 1 out of 80 planets are in that, beautiful, small enough habitable zone. Is that about a good number? And is there a number for G dwarfs? Courtney gave us for M dwarfs. Thank you.
There is no official agreed upon answer for terrestrial-sized planets in the Goldilocks zone of G-dwarf stars. This is a question that scientists will be working on over the next couple of years, especially using this catalog. What your first question was the number of the new terrestrial-sized planets that are in around G-dwarfs. I'd have to go back to that slide to count, but there are total of 10 candidates in total around G-dwarfs in this new catalog.
If I remember correctly.
Yeah, let Courtney address that.
I'd like to chime in and say that the reason why I'm so excited about Susan's results is that this catalog, because it was done in such a sophisticated, methodical way, really enables those studies of habitable zone planet occurrence for sun-like stars in the way that previous catalogs did not. So this is a remarkable step forward in our understanding of the frequency of terrestrial planets in the habitable zones of sun-like stars. It's laying the fundamental groundwork.
Still the number of the 10. I'd like someone to follow up with that.
So if I remember correctly, I think this is Seth, there's a little less than half of them that are around G-type stars. A little less than half of those 10. All right, let's take the next question from the phone.
The next question is coming from Lisa Grossman of Science News. Your line is open.
Hi, thank you for taking my question. This is for BJ. I was wondering if you could talk a little bit more about how you know that the Neptune-like planets probably don't have a surface, and then what the possible methods for formation for these planets are, and if there's something about their early histories, if we can tell anything about what makes a solar system produce an Earth-like planet or a mini Neptune.
Yeah, so we think that we can tell the difference between the rocky group and the mini Neptune group based on a few other lines of evidence in addition to the work we did. If you look at planets that are orbiting very, very close to their host stars with orbital periods less than about 1 day, those things could not have any atmospheres at all. They must have been blasted away. And we can see that those planets get no larger than about 1.7. If you go and measure the masses of a lot of planets in the Kepler field, you can see that typically planets larger than about 1.6 times the radius of Earth are low-density Neptune-like planets, and planets smaller than that are high-density. And then with this gap is just another line of evidence that supports this idea that you have these two different groups of planets. I'm sorry, could you repeat the second part of your question?
Sure. It was about how these planets develop and if there's a way to tell which stars are likely to produce the Neptunes and which ones are likely to produce the Earths, or if we know anything about the conditions that lead to one or the other.
Right. So we don't really know, but our best idea is that we had a population of planets that all start with somewhere between 1 and 10% of hydrogen-helium gases. So they all sort of have a range of various core sizes and a range of atmospheric sizes. Then when these planets, and the ones that I'm studying are all orbiting relatively close to their star with orbital periods shorter than 100 days, and we think when those are exposed to the stellar radiation, when you have this continuous population and you expose it to that radiation over many years, that tends to separate them into these two classes. The ones that started a little bit larger are able to hang on to their atmospheres, and they're the ones that end up as mini Neptunes, and the ones that started a little bit smaller and or had a little bit less hydrogen and helium to start with end up in the small rocky planets because their atmospheres get lost.
All right, thank you.
Great, we have another question online
Lewin
on the
of
phone.
Space.com. Your line is open.
Hi. So this is the final catalog from the first Kepler mission, but what can data you've been getting from the K2 mission, which looks at other parts of the sky, bring to these statistics?
I'm part of a team that's currently trying to do that, to use the K2 catalog to measure the frequencies of planets of different types. And one of the great things about the K2 catalog is that because it's covering a wide range of the sky, it includes many clusters of various ages, so you could study planet formation through time. And it includes many stars with different metallicities or iron contents, so you can study the role of different initial starting conditions on the planet properties. And it also contains many more low-mass stars than the main Kepler mission. And because I'm very interested in low-mass stars, I'm quite excited in what K2 can tell us about the frequency of planets at the small end of the stellar mass spectrum.
I'll just add that K2 not only gives you much more of a variety of different stellar types, but it also gets to probe different regions of the galaxy. So we could potentially see if these statistics that we're learning about the Kepler field are different in the different parts of the galaxy.
Great, we have one more question on the line. Caller.
The next question is coming from Irene Klotz of Reuters. Your line is open.
Thanks very much. I have two quick questions and then probably a little longer one. First one, I just wanted to make sure that when you said initially that this data completes the Kepler candidate list, just to double check that is not going to include any other data coming from K2. You're treating these as separate missions, and this data will complete the Kepler original mission. And then the second quick one is about, for Vijay, are there any proposed names for these classifications of planets besides Earth-like or mini-Neptune? And then I have one other one.
I think my answer is short. Yes, this is the last. The catalogs for K2 are completely separate from Kepler, and so this is the last time we're searching the data for candidates from the original Kepler mission.
As far as the names, yeah, we've been going with mini-Earths or mini-Neptunes and super-Earths lately. We had thought they were sort of all super-Earths, and it was difficult to determine which ones may have gas and which ones might have rocky surfaces, but now we have a clear distinction between the two.
Thanks. And also, either for you, Vijay, or for Courtney, why do you think that our solar system does not have any mini-Neptunes, and is there any reason to think that it might have at one time?
That's a good question. It is interesting that we don't have what appears to be the most common type of planet in the galaxy. Although you may have heard about a recent result of this potential planet that's far out in the outer reaches of the solar system called Planet 9. That one is potentially one of these super-Earths or mini-Neptunes, so it may answer that question.
Planet 9 isn't yet confirmed, correct?
No,
Correct.
it's not yet
Okay.
confirmed.
But
All right.
the people right across the hall from me are working hard to do
Okay.
just that.
Very good, very good. All right, I just want to remind folks in the live audience here, if you have a question, we'll bring a microphone to you. And while we're doing that, we will go back to the phone. We have one more question.
That's Bornstein of the Associated Press. Your line is open.
Yes, just two follow-ups. One, you guys said 50, around 50 habitable zones, smaller total or roughly 50 in the total. Isn't there an exact number? I mean, roughly could be 45 or 55. Don't you have an exact number? And second, just to put this all in perspective, Kepler has looked at a small part of the galaxy and distant part of the galaxy. Can you help us to, look at even the bigger picture, like saying you're looking at maybe 1/1000th of the galaxy? So if we wanted to take get a good sense of the rest of the galaxy, multiply it by what? In other words, thank you.
So I'll address the first question. We found we have 50 we have 49 actually high confidence planet candidates in the habitable zone that are less than 1.8 Earth radii. The catalog actually goes a bit deeper, but these candidates start to become a little less reliable, so we didn't want to present them here so you wouldn't see them as because they're not as confirmed or as validated as those others are. So I would go, the number, it's 49 that we showed on that plot that you were looking at. In terms of the fraction, do you have a better idea of that math?
Well, it's 100 square degrees, right?
Right, it's 100 square degrees. So 200,000 stars is all we actually looked at, though.
Not that. Can I answer that?
Absolutely.
No, the Kepler field is approximately 115 degrees square, and that's about 0.25% of the sky. So in fact, you need 400 Keplers to cover the whole sky. So that's the question that if we assume the statistic, the signals field and all the field that K2 has observed are median, and we can multiply by 400 to get a sense of what the whole universe or galaxy around part of the galaxy that we're observing. But we haven't done that. This is very recent information that was released this morning. So I'm sure there will be a lot of people that will study the planet demographic based on with the information on this catalog in the future.
We can also cheat a bit and look at the results of the Transient Exoplanet Survey satellite mission, which will cover almost the full sky. That has 4 cameras, each of which has a field of view of 27 by 27 degrees. Most of those stars will only be observed for 27 days, but some of them will be observed for up to almost a full year. So we can then cross-compare what we see with tests for short period with planets with what we see from Kepler and really check to see how planet properties vary across the full sky.
I'll just add that one problem with sticking to a real strict number of the number of planets in the habitable zone is that these boundaries are all very fuzzy. The actual boundaries of the habitable zone at the inner and outer edge are not that well known, and even if they are very well known, there's a range. It's not a sharp boundary. It's fuzzy.
And in terms of multiplying that out to the galaxy, those 50 are transiting planets, right? And there's a big difference in transiting and actual the intrinsic population.
Right. For a planet like the Earth in the habitable zone of a star like the Sun, there's only 1 chance in 200 that planet would appear to transit.
Great. All right, we have a couple more questions on the phone.
The next question is coming from Tracy Watson, USA Today. Your line is open.
Thank you. I wanted to ask about KY7711, if I've got that number right, because you said it sits right next. It receives about the same amount of insolation as Earth, and it's 1.3 Earth radii. Can you put that into context for me? How does that rank it then in terms of Earth twins? Is this now the closest? I can't remember the statistics. And the second question is about the kind of 2 flavors of planets. Is there any reason to think that that these 2 flavors are different in other parts of the universe, or will this rule apply elsewhere? Thanks.
So 7711 is the closest to the Earth in terms of our current measurements of its size and how far away it is from our star. And so as a result, it gets approximately the same amount of heat that we get from our own star. However, there's a lot we don't know about this planet. And as a result, it's hard to say whether it's really an Earth twin. We need to know more about its atmosphere, whether there's water on the planet. I always like to remind people that it looks like there's 3 planets in our habitable zone, Venus, Earth, and Mars, and I'd only really want to live on one of them.
And just to clarify, Kepler can identify what properties of a planet?
We directly measure the size of the planet and how far away it is from the star.
So we don't know if it's habitable.
So we do not know if it's habitable.
All right. We have a couple more questions on the line. Let's go there.
The next question is coming from Nell Greenfield Boyce, NPR. Your line is open.
Oh, hey, thanks for doing this. Just to confirm, so I'll take the roughly 50 number, but I just want to make sure that the 10 you're announcing today are in that number. So it's not roughly 50 we knew about in terms of candidates in the habitable zone and the small, potentially rocky size. It's more like, now in total we have 50, which includes these 10 that you are announcing today. And the other question I had is, so if this is the final batch of data from Kepler's original mission, I mean, how are you guys feeling now? Do you feel sad? Like, I guess we've all gotten kind of used to these big, downloads of, dumps of potential planets where, 200 potential planets just isn't really a big deal anymore. I mean, is this like kind of the end of an era for planetary hunters, or what do you think about that, since this is going to be the last one from the original mission? Thanks.
So to answer your first question, the 10 are a subset of that 50 that we're talking about. So we found 10 new ones, and that makes up the 50 as part of that 50. Yeah, it feels a bit like the end of an era, but actually I see it as a new beginning. It's amazing the things that Kepler has found, and it has shown us these terrestrial worlds, and we still have all this work to do to really understand how common Earths are in the galaxy. So I'm really excited to see what people are going to do with this catalog, because this is the first time we have a population that is really well characterized, and we can now do these statistical studies and really start to understand the Earth analogs out there.
Thank you.
The next question is coming from Lisa Grossman, Science News. Your line is open.
Hi, thanks for taking another question from me. So I just wanted to follow up a little bit on Seth's first question. So Kepler's chief mission was to get a number for this fraction of sun-like stars with Earth-like planets, and you're not releasing a number like that today, but you are releasing the final catalog. Here's all the planets we're ever going to expect from Kepler. Is that enough to get that Eta Earth number? Is that going to get us there, or is there more that we need to do? And why are you not presenting any number for the fraction of sun-like stars that host Earth-like planets today?
Well, that's a great question to address the importance of this catalog.
I've already forgot the beginning question. Yes, we absolutely have enough to do those studies. We have a population of high confidence planets that are terrestrial sized and in the habitable zone of sun-like stars. The reason we haven't done this is this analysis is very complicated, and there's a lot of pieces that go into it, but at least we now have all of those pieces. And scientists will spend the next year talking about how to get to the most accurate number and the best way to go about it.
Great, let's go to a question here we have in the live audience.
Did you find anything anomalous when you were looking through all of these all this data? There was some talk, I don't know, several months to a year ago about a potential giant artifact in space. Did you see anything that you can't quite explain?
Could you clarify a little bit what
Well,
giant
there was
artifact
a
you're
well-known
talking
news story that came out, I think, about a year ago, and the what?
You're talking about,
The big sail, the sailing alien superstructure. Yeah, that's it. Thank you. Yeah. So, without specific regard to that, were there anything? Did you find anything out there in the vastness of space that you can't account for according to what we know in science today?
The light curves from Kepler are truly unique. The way we did the search means that we really just find things that are similar to planets. And so this catalog itself, I didn't find anything where I just absolutely could not explain what I was looking at. But that said, other people have mined the Kepler light curves looking for other interesting things, and that's how they found that star with the large changes in brightness that happen. And they're continuing to observe that to figure out what kind of star that is. I think I just saw on Twitter that it's decreased in brightness again by about 2%.
So nobody's quite figured that one out yet?
As far as I know, no.
Thank you.
Great. Well, we have a number of questions also that have come in through social media and on Twitter, so we'll go there. Take a couple questions. The first one comes from Doug for Far Worlds. Are there any Kepler candidates to be announced today or otherwise that are circumbinary terrestrial planets? Now, maybe we could answer what a circumbinary planet is to start off.
Kepler did find about a dozen, I believe, planets that go around a binary system. So there's two stars going around each other, and then there's planets going around that binary system. Because of the way this catalog was created, we are not set up to find those very interesting systems.
But you said there's about 12 that we found so far.
I believe that's the number today.
All right. Let's take another question here from social media. This comes from @TSA Malofto. How long do you estimate Kepler to remain upright or in orbit? And would it live till TESS launches and its science mission starts? Maybe that's one for Mario. Yeah.
Yes. Now, as we mentioned here, Kepler is still taking data, and we're on the K2 mission, which is a secondary mission which we have been doing for the last 4 years. This mission can only observe for about 80 days a determined field around the ecliptic plane of the galaxy. We expect to have, for sure, fuel until our campaigns, campaign number 16. We are in campaign number 14 right now, so and about the end of this year, starting next year, we'll start campaign 17, which we don't know if the fuel is the main limitation that we have with Kepler. It's very hard to measure the fuel in space, and for that reason it's being done indirectly. But we expect to still be observing during the year 19 and possibly even beyond that. Now, TESS is going to start flying next year in 2018, if possible they overlap. However, I think the overlap probably is only nominal. There's not really significance. Since Kepler still will keep observing a small piece of the sky around the galactic plane, and Kepler will, in TESS, will do all sky survey, both of the northern sky and the southern skies. In the first 2 years of TESS will be done 1 year doing the southern sky, and the next year be doing the northern sky, and later will be pointed observations. So TESS will be doing a completely different mission, and the target population of TESS will be mostly nearby and very bright star, which different from what Kepler has been doing even during the K2 mission.
Great, thank you. Here's another question from social media from @Playtime with Kess. Just to confirm, we can only see planets whose solar system's elliptical plane is aligned towards our planet. Now, what do you want to take that and just distinguish between the transiting worlds and?
That's for this particular method of detection where the planet passes between us and the star, but there are other detection methods, for instance, the radial velocity method, that are sensitive to planets that are in different orientations. So we're able to piece together results from different types of planet detection methods in order to see planets that aren't just perfectly aligned with us.
Great. I believe we have one more question on the line. Actually, we have a question here in the room. There you are.
Hi, Matt Bigler, KCBS, CBS News. My son turns 4 this week. He's getting his first telescope. It's actually a type of spotting scope, but it'll count as a telescope. Could you explain to him what your announcement is today why it's important, and I think if you do that, that will help me explain to your average news consumer what it is that NASA is announcing today. Thank you.
You think this would be easy because I have a 5-year-old at home. So what I do is I work at the airport is what he thinks I do. So what's exciting about today is we have taken our telescope and we have counted up how many planets are similar to the Earth in this part of the sky. We took our telescope, looked at the sky, and we said, how many planets are there that are similar to the Earth? And with the data I have, I can now make that count. And from there, we're going to determine how common other planets are. Can we find, are there places that we could live in the galaxy besides this place that we call home? That close?
And as far as my result, I think it may be a little easier to describe it as far as planets. It's just like, or as animals. It's just like when biologists discover a new species of animals. In this case, what we thought was a single species of animals is in fact 2 very different things. So I think that boils it down pretty nicely.
Great, thank you. Let's take another question from online. This comes from Von Bismarck. How big would an orbiting telescope like Hubble need to be to get photos of these distant planets? Maybe we could expand a little bit, and we're talking about the future now and those steps to get to that point.
I think it's important to keep in mind that when we talk about directly imaging planets in the habitable zones of nearby stars, we're not talking about making a beautiful picture like the one you might hang on your office wall. We're talking about collecting enough photons from this planet to fill a pixel in your image, and then you study that image over time and try to make guesses as to what the surface could look like based on the features you see in the planet. For the telescope designs we're considering for the 2030s, we're thinking about things that might be the size of, say, 45 feet across. And that wouldn't give us a picture of the planet, but it would give us the information we need to assess whether that planet might be someplace that's hospitable to life.
All right, thank you. Let's take another one from social media. This comes from PC415. Have any of these planet candidates given any hint as to having large moons or ring systems?
We did not find any evidence of moons or rings around our planets in this particular catalog.
And those are even more difficult to discern in the data.
Extremely
but there are
difficult
folks
to
out there
find.
looking for them. Yeah.
Yeah, and there are.
Great. Here's another one from social media. At TTCats, which is the nearest planet, exoplanet, and how far from us is it?
Proxima Centauri b. It's the planet around the closest star.
And that's about 4 light years?
Yeah.
Great. Right. All right, I think we have one more question on the line.
The next question is coming from Seth Bornstein, The Associated Press. Your line is open.
Thank you again. Sorry to keep asking these questions. Can I ask most of the panelists or all the panelists just to go back 8 years, 9 years before Kepler was launched? Had you been told you would find 50 Earth-like, rocky planets in the habitable zone, is that a number? If you put yourself, would you be disappointed with 50? Would you be more than surprised? Is this beyond what you expected? Just to put, in other words, is this more than you expected? Is this less? Is this about what you expected? A sense, if you go back pre-data. Thank you.
This number could have been very, very small. And I, for one, am ecstatic that we've found 50 potentially habitable worlds orbiting nearby stars. That's great.
Yeah, 8 years ago, I was just starting out in professional astronomy, and we definitely knew very little compared to what we know now about the population of exoplanets. We really had no idea how common Earth-like planets were, and so that's why we made the Kepler mission, was to answer that question. And we're still working on that answer. It's very difficult. There are many groups that have come up with numbers, and we're starting to converge on the final answer. But I am definitely ecstatic that we've discovered that amount. I think that is definitely a nice number that I would have hoped for.
Great, and that number of 50 is from what Kepler was able to observe. Now the actual number, the intrinsic number in the galaxy is, we're talking in the billions. Yeah. Okay, I think we have one last question on the phone. Go ahead.
The next question is coming from Jonathan Callahan, IFL Science. Your line is open.
Hello, thank you for taking my call. I have a question regarding finding Earth analogs. As I understand it, this is Kepler's end of its 4-year mission. And to find planets similar to ours, we need to see 3 transits, so 3 years of observations. Are there any more missions planned in the future to find similar planets on similar lengthy orbits? Thank you.
The Plato mission out of Europe will have the potential to find planets in very long period orbits, because that mission will be staring for roughly 2 years in certain patches of the sky, as well as doing another set of steps where they look at fields for less duration of time. With the TESS mission, depending on what they choose to do in year 3 and beyond, perhaps they could also find planets in very long period orbits. But one of the pathways we're considering going forward is finding a planet with a transiting survey, whether it's Kepler, K2, or TESS, following up with other missions, perhaps using radial velocity from the ground to measure the mass of the planet, and then doing targeted observations of that particular star to confirm it. So we don't necessarily need to use the same spacecraft to see all 3 transits. Mario, did you have something you wanted to add?
Yes. Let me remind people that the first exoplanets were found only about 22 years ago, so it's a very young field. And NASA is very interested in continuing this path. The announcement we made today really is the beginning of this path into continue searching for new worlds and finding signs of life and beyond our solar system. NASA has a path to continue studying. Right now we're studying 4 large mission concepts, of which 2 of them are capable to do great work and advance the field of exoplanet. However, we don't ourselves determine the type of mission we're going to do in the future. This is it's a task given by Congress to the National Academy of Sciences, which every 10 years advise us to continue with this plan. So in 2020, we'll be here and we have high expectancy that several of these activities, including probe mission, which are mid-sized class like Kepler, or large mission, will be recommended to the agency, to NASA, to continue this search. So we are really at the beginning of this path. Although Kepler was launched about 8 years ago, this field is only 22 years old. Really, we'll be continuing this search for life. In fact, within the agency, the Earth 2.0 is an iconic goal that we expect to reach maybe in the next 5, 10, or 20 years. But let me say, one theme is important for us is, are we alone? And maybe Kepler today had told us indirectly, although we don't have confirmation, that we are probably not alone.
Let's take one more question, and then we're going to wrap up for the day. The question's coming from social media. It's regarding James Webb Space Telescope and that next step. So JWST is scheduled to launch next year. How many of these planets will be priorities for atmospheric study? Maybe you can explain that just a little bit briefly. Mario, is that something you can take?
I would say all of them, although a few of them are already in the queue to be observed. In fact, many of the Kepler most interesting targets are already part of the early science release, in which 4 of the instruments of James Webb will be pointed starting during even the commissioning time after the launch in November 2018, next year. So I would say all of them, as the community advances in the new observing cycle of James Webb, will be able to inject this target to be followed up by James Webb and the many other spacecraft observing. For example, I remind you that Hubble still observing, is in the 27th year observing, and will continue for many more years to go. So Hubble and Spitzer hopefully will be observing for a few more years, will be very helpful in this path of characterizing this very interesting new worlds.
Great, thank you, Mario. Very exciting steps on the horizon on our way to confirm whether or not we are alone. Well, we'll wrap it for today's briefing. I'd like to thank the panelists for sharing these exciting results. I'd like to thank everyone here in the live audience, and for those of you joining on the call as well as online. If you joined in late, don't worry, we have the materials that you heard today and a recording of this press conference online at www.nasa.gov/Kepler. If you'd like to follow us on social media, you can find us on Twitter at www.twitter.com/NASA Kepler, and also on Facebook, www.facebook.com/NASA's Kepler mission. So thanks for tuning in and sharing in the thrill of discovery at Astra.